Welcome to the second part of their artificial intelligence beginners level program. So, in the last class, we were seeing about the plan of attack, the reinforcement learning, and the Bellman equation. So, following that, we'll start with the plan. Okay, the plan. What is the plan? So, in Bellman equation, we were just assigning some variables to each of the steps, right? So, if I just go back a little, I can see I have assigned each of some variables, right? So for this step, v is equal to 1. That means value is equal to 1. For this, value is equal to 0.9. So for this, we have value is equal to 0.81. Using Bellman equation, we were assigning some values to the corresponding path so that our agent, the agent in the sense the thing which is using that artificial intelligence, will be moving according to that. Suppose it is here, then it will be moving here because it compares both the value. It is 0.66 and 0.81, right? So it compares both the value and it will move on to the greater value, right? So if it is here, it moves on to here, and then if it here, it just compares the possibility here and here, and then it moves here, and then it just, once it reaches this state, it just compares this and this. So it is this and this will go here, right? So what is our plan here? So what was our plan here, right? So we have determined using a Bellman equation, and we have just determined some variables to each and every state. Consider if it is here, it will jump over here, and then from here it will move on like this and like this. Right? So our plan is, if I'm here, it will just move on to here, here, here. If it is here, just compare with this. Here means in this cell means this, right? This, and this, right? So this is our plan. So this is the plan of the agent, right? So wherever it is, whichever state it is, it will follow the plan. Don't confuse with plan with the policy. A plan and a policy are more or less similar, but it's not the same thing. Okay, so you just think what is mean by, like, you just understand what is mean by plan as of now. So plan is nothing but the way the agent is going to execute, or the way the procedure, okay, the procedure the agent is going to follow is called the plan. Okay, so we just had a look at the plan. Okay, what else next? Okay, so we just move on to Markov decision process. So what is mean by Markov decision process? So we have a plan here, right? So if agent is in here, it will just move on to here, then here, here, and then here, right? So if my agent is here, it can just move on up, and then up, and then right, and then right, and then right, and move here. Right? So how it was coming? So it was in this cell. It have a chance to move up, then up again, and then right, and then right, and then here. Okay. So it has, if it is here, it has only one go, right? So if it is here, it has only one chance. Like if it is here, suppose consider if it is here, it has probability of moving to 50% this side and 50% this side, right? Both are same, right? See, if we just compare before, if it is here, a 50% of chance moving here, and then 50% of chance moving here, right? So if we have, if we from here 1 2 3 4 5, which is same as here 1 2 3 4 5, both are same, right? So we have 50% of chance for our agent to go here and here, right? So but if you it is here, what will be its position? It have a deterministic search, like it have only one go, 100% it will be going this side, right? So we can just divide the search of an agent into two types. The first is deterministic search. Suppose a agent is there and it have only one go, means it will just move in up direction. So 100%, like we can just say the next move of the agent is 100% towards the up, right? So that we used to call a deterministic search, where the possibility of moving is 100%, right? So the next type is non-deterministic search. Okay, what is mean by non-deterministic search is, if an agent is there, it has a probability, something like it has three ways. The one is it can move 10% in the right side, 10% in the left side, and 80% in the up. So it has three probability. It can move in all three directions, whichever three direction it wants, it can move. So it has 10% probability of moving left, 10% probability of moving right, and 80% probability of moving up. It can move this side, it can move this side, it can move up. Okay, so it can move up by 80%, it can move left by 10%, it can move right by, and it can fall in pit by 10%, right? So every time we cannot get a deterministic search, right? In a practical point of view, suppose consider like you are assigning some robot dog, it doesn't have 100% thing, right? So if it is a 100% thing, it won't think, right? So it have probability, either it can do this or do that. It have probability, right? Okay, 10% is chance of falling into the pit, 10% of moving into left, and 80% of moving up, right? So it has, every time we will be having a deterministic search. For that only we bring the concept called Markov process, and the other term Markov decision process, that is called MDP. Okay, so what is Markov decision process? Okay, a stochastic process has the Markov property if the conditional property distribution of future states of the process, conditional on both past and present state, depends only upon the present state, not on the sequence event that precedes it. A process with its property is called Markov property. And I'm telling you, you don't want to break your head into this. I'll just divide this sentence, or I'll just divide the statement so that you can just easily understand, but you don't get confused, like a condition on both past and present depends only on present state. You don't want to mess up that. Okay, so what they are saying now, okay, so you just check. Okay, you're going to check now. So as we see here, the stochastic process that a Markov property if conditional property distribution of future state of the process. Okay, so we will be determined if the thing is here, if the agent is here, we don't want to see how the how the agent have reached here, whether it have came from here to here, or here to here, or here to here, here to here. We don't want to search. It is none of our business. Okay, we are going to see only the probability, the possible ways it can move. Okay, the possible way it can move. We don't want to see about the past thing, how it have reached this state, the preceding values, the preceding state and all, we don't want to mention. Okay, so when I just see it want to go up, it has a probability of three things. Consider like it can go hit into the wall and it can be in the back, it can go into this 10%, it have 80% of moving up. Okay, so it has, if it is a non-deterministic search, it have probability of three things. It can move up 80%, it can hit the wall and can be in the same cell, or it can fall in the pit, right? So what does this Markov decision process or Markov process says is, If an agent is present in the particular state, you don't judge or you don't want to calculate what was from which state it was to from which state it came to this state. Okay, you don't want to check that. Okay, so that was the thing. So here you can see condition. So conditional probability distribution of future state of the process condition on both past and present date depends only upon the present state, not on the sequence event that precedes it. Don't think of the things and how it reached that state. You just think on how it gonna proceed. So we are going to see here only the things, only the probability of moving further, not the thing, how it came, whether it came from here to here or here to here. We are not going to see that. Okay, so the Markov decision process. What is meant by Markov decision process? So Markov decision processes provides a mathematical framework. This is the keyword of this. Okay, so it is a mathematical framework. Okay, basically a Markov decision processes is a mathematical framework for modeling decision making in situation where outcomes are partly random. We said no non-deterministic search. Only one option is won't be there. So random option will be there. Randomness will be there. Okay, under partly control of the decision maker. Who is the decision maker here? So the agent is the decision maker. The robot, or the robot dog, or the robot which you are going to interpret with artificial intelligence is the decision maker, right? So Markov decision process is a mathematical framework. Basically, it is a mathematical framework for modeling decision making in situation. Consider agent is here. It want to move up. What and all probability it has? It has a probability of moving in all four directions. So here it comes, it gives a question where I want to move. Where I want to move. So it doesn't have only one way, it has four different ways. If it is a deterministic search, something like we just saw in a last class or last video, it is something like, okay, the values are fine, I can just move on, I just can move on to the greater values. That is something a deterministic value, right? But most probably in real-time environment, we make up with non-deterministic search. So we'll have probability or we have randomness to move here and there. Okay, so here comes the questions for the agent where it want to move. So a Markov decision process is involved in this. It's not a big deal. So we just saw Bellman equation, right? So value of the state is equal to the maximum action corresponding to the state and the reward, right? Plus discount factor of the value of this previous state, right? So Markov decision process is something like an add-on, to it, to the Bellman equation. So what is have? So we have a preceding, right? A preceding, like we have considered to be, we have in this thing, we have three things, right? So the probability of moving left is 10%, probability of moving right is 10%, the probability of moving up is 10%, right? So we have three. So consider like that. Okay. So we have three state, S1 prime, S2 prime, and S3 prime. So we have three probability or randomness. Okay. So for that, we have the corresponding value. Okay, so now what we are going to do, we are going to entirely remake or rebuild the Bellman equation, right? So what is the probability of going to the first state is 80%, right? Then it is 0.8. Second state is 0.10% means 0.1, and the third is 10% again. This is 0. Again, right? So I'm just adding this. So 0.8 times of this state and 0.1 times of this state and 0.1 times of this state. So I was just replacing that. So when I just try to rebuild, my equation becomes much simpler and this in this way. It is something similar to this. You can check. So value of the state is equal to maximum action of R, which is reward of state correspond to the corresponding action. Same, right? Maximum value of R, which corresponding state and action, plus discount factor times of 0.8, which is the summation of this state and then action and its corresponding state, right? So we just make the same thing in a we just what to say, we just derive or we just make it simple as an equation, right? So now what we did, so we had a Bellman equation, suppose like this, and what we did is we just we just added Markov decision process, which will be dealt with randomness, right? Means a non-deterministic search, right? So we just use that and we have rebuilt in this format. Okay, so this is all about Markov's decision process. Now, in the Bellman equation, if it is a deterministic search, if it is a theoretical problem, it's well and good. But if it comes to real world environment, we should add randomness. The robot will have an option whether I want to move up this side, that. It wants to think. It has the probability. It has that randomness. Okay, so it will be thinking, oh fine, I just have three things, what I'm supposed to do. I don't have a deterministic search, right? So it will be thinking. Okay, so I have an additional reading for you here. So we have an paper called or a publication called a survey of application of Markov decision process, right? So you people might ask, okay, you are just saying about some randomness or some probability, n number of probability, right? So what really this Markov decision process is involved? You can just check in the table the application areas, the population harvesting, right? So population harvesting, agriculture, the major thing is that investors will be doing, right? So they will have some goals. Suppose a share is something, they expect some share will be increasing. They can just they can't blindly go on that share. They will be investing in some other else also, right? So what they will be doing, they will be doing 80% of the share in the confirm through, and then just 20% in some other through, right? So they have some randomness in that. Okay, they have some randomness in that, like that overbooking, epidemics, credit, sports, patient admission, everything we have randomness, or we just give it to the machine to predict that randomness. Okay, so I have attached the link here so that if you are further interested to know about the Markov decision processes, you can just visit here. Okay, so we'll move on to the next thing, which is what is the difference between the policy and the plan, right? So we just have rebuilt the Bellman equation with adding some Markov decision processes, right? So we have got a new equation to solve or to just predict or to just uh, get the value of the state, the value of the corresponding state, right? So if it is a deterministic search, we got something like use the raw Bellman equation, and we have just predicted this, right? So which will be 1 and then 0.9 and 0.81, and then we have something like this, right? So what will be its plan? We just see, right? So plan is something like if it is here, then it will be moving here, and it will be moving here, here, and then here, right? If it is the same condition, if it is here, it will move here, 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 and then here. If it is here, it has two probability, it can move here, here. If it will move here, right? So this is what we call plan, right? So this is what we call it as plan. So if it is here, it will move like this to the state. If it is like this, it will move like this to the state. If it is like this, it will move like this to the state. Getting that what is the plan? Now, I going to apply this equation now. Okay, when I use only the raw Bellman equation, I'm getting this value, right? Suppose you consider this value of the state is 1, and if you just see here, it is 0.9, which is somewhat, which is equal, right? Which is equal to this. And if you see this and this will be equal, this and this will be equal this, because it just calculate the preceding on how it come. So it came from this one, this one, this one, this one, this. So it will be somewhat equal, but I'm going to apply. So I'm going to apply the Bellman equation where I have added in the Markov decision processes. Okay, so I just move here. You can just see here that we don't have the value to be 1 now. It will be something like 0.86. How come? You can just compare with this. So when I add this, it is something new. Okay, it is not 1. And the same time, if you see 0.76, here 0.39. Oof, it is something double, right? So here it was equal, and here if you see, it is something double than this value. You're getting that? See here, it is something double. Okay, so when I have this raw Boltzmann equation, you can just see what was my plan. This is my plan. Okay, this is my plan. So if it is here, it will just go here and here. Okay, but we have a probability, right? We have randomness, we have multiple choices to choose. So what will be my policy? When I click here, when I see for this first time, I'm not see, I understand only one thing. Even artificial intelligence can work, can think better than a human. This is what I'm not surprised or something. I got to know like artificial intelligence is somewhere one step ahead of human thinking. Why? Because if it is human using, we got this right. So if it is human, what will be thinking? If we are somewhere here, it will just compare this value and this value, and it will go here, right? So its direction is up, right? It has three probability, 1, 2, and 3, right? So what it will thinking, will keep the arrow here, right? If it is here somewhere, if it is somewhere here, it will just compare here -1 and 0.36, which is, this is great, and then it will move here, right? But what we have, see, the arrow mark is not upward, it is this side, and here also the arrow mark is not this here, and here if you see it is 0.36, it moves here. Why it is so? Okay, so here comes the thing which what to say, which an artificial intelligence or the agent will think better than this, because see here, so what was, we'll consider this state, why it was here, not an upward arrow. So we have probability, right? We have probability of moving up, right? Moving up is 80 percentage, moving left is 10 percentage, moving right is 10 percentage, right? So what it does is, if it is upward, so it has a probability of moving into the pit 2. So it want to eliminate that. So what it does, so it faces this side. So if it is 80 percentage means, if 80 percentage means 10 times it is hitting, 8 times it moves this side, and 1 time it moves this side, 1 time it moves this side, right? So 8 times it will get hit, and it will come to here position only, and in the 9th time it will just move on to this and follow this path. Okay, or else if it is in 9th position, it will just move on to here, it will just go on here, do that. You can just see here. Okay, so it will just get hit, and it will go in the like this path, or else like this path. Now you can ask, I am here, I just want to proceed 1, 2, 3, 4, 5, 6. Rather, I can just go from here 1, 2, 3, 4. Why I want to choose the biggest part? The question arises, why I want to choose the biggest path? Okay, so you can see here, if I am here, if I just move here, if I just choose this path, if I should go here and then go here, then I have a probability of getting in that pit too, right? So I have a probability of getting into that pit. So it tries to eliminate. I don't want to take the chance. I don't want to take that randomness too. Rather I can just take a longest path even, and I can go safely. Here also it has three things, right? So sorry, two things, right? It can move left or it can move up, right? So it will just eliminates. It can move up, it will hit for 8 times, and the ninth time it will fall here, and then it will just follow this. Okay, so this is where we can just imagine how the agent is something like they are just what to say, they are one step ahead of the humans. This proves that, right? So if it is us, we'll just determine something like this. So probability will get 8, anyhow we'll be going that. That was our thinking. But data says, suppose out of 10 move, what if your first move itself is right? So you will fall into the pit until the game is over, right? So it eliminates, it try to eliminate everything. So even though if it is 8 times it gonna hit, after that it will move either to left or right? So after that it will just follow the same path. Even if it moves here, it will just follow this path. Even this is the path. So it won't take at that 0.1 percentage, what to say, 0.1 percentage also, it won't just it won't try to fail it. It will just overcome with this. Okay, so this process is called the policy. What is the policy of the uh, agent? So it doesn't want to just fail in the game. It just don't want to get a penalty. Okay, so it will try to come out of the situation. It try to eliminate the loopholes of the situation. So this is the policy. You can just think what is the plan and the policy, right? So moving on further, the living penalty, right? So what is mean by living penalty? So we know what is meant by penalty, right? So whenever we do something wrong, we should do something, right? So if at all you just do some, you have some, what to say, if you didn't drive properly, if you're not good at a road, the traffic police obviously will penalize you, right? So the same things, we should assign some penalties to our agent in order to avoid some mistakes, right? So what we were seeing before is if here, okay, here, if the agent is here or agent is here, instead of moving like this, it will take the longest route, right? So by taking such a route, what we can avoid is we can avoid the probability or randomness of not getting fall into the pit, right? Of not getting fall into a pit, right? So but at the same time also we should take care of some things. Suppose if I assign something considered to be in this game, something like if I keep here, it is also some disadvantage. Even though it doesn't go like this, it also has some disadvantage, like it's going at the longest path, right? Even though it just safeguards it, like it eliminates the randomness of getting into that pit. It just do this other thing, right? So what it is does is like it takes the longest path. So how to overcome that? Okay, so what we are going to see is living penalty. Okay, so again we come to the Bellman equation, right? So the value of state is the maximum of action to the corresponding what to say reward we will be getting at that state for that action, plus gamma times, which is the discount factor, times of probability of the certain state for a certain action, and that the upcoming state, right? So value of the upcoming state too, right? So as we saw before, What is that? For in an agent, for an agent in an AI, for every action it does in an environment, there is a state and reward. Okay, so if an agent does an action in an environment, suppose it moves like this and the like this, like this, like this, and like this. At the end of the state, what is said? It was in this cell, and the reward is like it doesn't come out of the maze, so it got -1. Right, so every action, if it is that, means that is fine. So if it comes like this, something like this, and come out of the thing, the reward will be +1, and the state will be out of the maze, right? So for every action will be having some equal and opposite reaction, right? So for every action in the, for an agent in this environment, we have a state and we have corresponding reward. We are taking this example, right? So in this game, this agent should propagate through these cells without falling into the pit, which is, if it falls, it gets -1, and if it didn't fall, it gets +1 when it's reached it. Okay, so we gave some policies and plans for the agent. Now we are not going to reward the agent only if it reached these two positions. Suppose if it moves like this, until unless it moves to that position, we didn't reward it anything, right, until now. So if it goes here, it will get +1. If it goes here, it gets -1, right? So what we are going to do now is, we are going to give some penalties for the agent, so that it won't take that longest path. It will just try to something like, we'll just some more restriction for it, so that it will just consider that assumptions too. Okay, so what we are going to do, see, I'm going to give some penalties. Okay, so consider like, if this agent is here, something like that, when it goes to this, it gets a penalty of -0.04, this -0. This, and then it will go here. So it won't take the longest path. It will try to figure out which is first. What it will take, first it will prepare a plan, and then it will prepare a policy based on the probability or randomness, and then it will, third thing it will take, okay, if I go for more moves, I'll get a penalty. So considering the three things, it will just get a one path. So when it is here, it won't get a penalty. Suppose consider it goes here, it will get -0.04, and again if it goes to here, it will get this penalty. But by usual, when it is present in that, it won't get that penalty. Okay, so now it is, what is going to do is, so if it goes like this, -0.4, -0.4, -0.4, -0.4, and then it reverts like that, it will go. Okay, so I'll show some penalties and how this reacts with corresponding some penalties values. Okay, so here I have some reward, what to say, penalty values for every state. Every state, if it reach, it gets penalty of 0. That means no penalty. So what it will be, what it will how it will go. So if it don't have any penalty, it has two consideration only policy and plan. So how it will react, in the sense, it will be like similar like before. So it will just consider only, I should not go to this way, I should not choose this way. So it will just hit in this, and then the probability, it will go here, and it will go like this. So if it goes like this, also same reward points +1. If it goes to this, also same reward points +1, because here no penalty on reaching how many steps, right? So second, we have a reward point -0.04. Then see what it does. What it does. See here, it is something similar, but when I just place, if it is penalty is 0, if I place here, it has, if it is something like this, it will hit in the wall 10 times or 8 times, and then it will move here or here. But what here it is showing, see, if it is hitting 8 times, then it will comes -0.04 into 8. So it penalty get increased. So what it does is, it just adjusts itself so that probability of getting this also is fine. because okay, so it's just assigning here. It's not, see, it's not here. If it can hit 8 times and it can go here or also here, but see here its first priority is moving up. You don't want to choose here, because if you choose here minus 0 0.4 1 2 1 2 3 4 5 6 7 8 something, is like more than the value, right? We can just go here. It just go minus 0 0.4 and 1. See here also, see, it will just go here like this. It will just go here like this. Okay, so I'm just increasing my penalty value into, see, it's 0 0.04. It is something like half. Just see what happens. So here, if I keep here, it will just travel like this. But see here, if I keep, it's thinking better not go to like this, better like go to like this. Even here, if I just keep, it will be something round. But here, see, it is like this and this. Okay, if suppose if I keep something like it minus 0 0.5 minus 1 minus 1.5 minus 2 minus 3.5, I will get nothing, right? So but here if I keep minus 0 0.5 minus 1 minus 1.5, then 1, it is minus 0.5, right? So it is something getting more rewards. So it's just adjusts itself for that. So if I keep minus 2, what will be the thing? It's saying, see here, see clearly here, it's saying it is minus 1, rather than I am going here which is minus 2, I can fall into the pit which is minus 1, which is greater value than that, right? See here also, see, instead of going here for minus 2, I can jump into the pit whose value is minus 1. See here, another thing you can notice that here it was like it can go here or it can go here. But see now when it was minus 2, it's calculating minus 2 here, minus 4, minus 6, minus 8, and then plus 1 means minus 7, right? For a see, minus 1, minus 2, minus 4, minus 6, and then minus 7. Both are same. It takes the shortest path. Getting that? So we assign some living penalties. So whenever it does, instead of giving rewards at the end of the goal, we are just giving some sort of what to say, rewards, or in terms of penalties for them to attain something, to have some restriction. Instead of doing a big work, we just find which is a smarter way. Okay, instead of going around like that, you can just get the smartest way out of it. Okay, so this is what we called as living penalties. So we'll be assigning each and every state, for each and every state we'll be assigning some penalties for that. Okay, so we'll jump on to the next topic, which is QLearning intuition. What is meant by QLearning? What is the word Q refers to? Okay, so QLearning, basically QLearning is something like we just started in the last class, right? So these are not like pre-programmed. Once they start doing their work, they'll be learning from, like if at all we consider a dog, right, as a robot dog. So if it falls, it will just take it as, okay, it's not a, it's a negative reward, so it will just neglect that, and next time onwards it won't do. That is called learning. It will be learning until, like if it do some mistake, it will be keep on learning. It won't stop, right? The same way, this thing, QLearning intuition, is something like for every move, for every state, it will be keep on learning. Okay, this I have done, this I have done. So for that I get this reward. For this action, I'm going to this state and I'm going to get this reward. So it will be keep on learning. Next time it will just predict the best way out of it. Okay. So as we saw in the Bellman equation, we have, right? So we have the value of here, the value of state, and then maximum action. For that we are getting reward for certain state and certain action. For that corresponding we are getting reward, and discount factor times of the probability for the state and then action and the next state, right? So you are saying something, Q learning, where is the Q? People might ask, where is the Q? So let me take the same example. Okay, suppose consider this agent is present here. It has three probabilities. Okay, right? So it has three probability, that is called randomness. So it has it can move to V1, sorry, S1 state, S2 state, or S3. Okay, so it has three values, 1, 2, and 3. But Q is nothing but, for every values you are going to get, as we said before, right? For every action, the action in an environment will be getting a certain state and an action, certain rewards, right? So for that, we are going to calculate, instead of considering state, the corresponding action should also be noted. Okay, so the basic difference between why V and Q arise is, V is nothing but something value, and Q is not determined till now. It is something a practice to initiate. To be frank, that is the thing, because there is no evidence like why Q, the letter Q was introduced. Basically, getting more, we get to know that Q was about to say about quality, not nothing more than that. So you don't want to mess up why the letter Q came here. Okay, so Q is about quality. So Q learning is about the quality in the learning by the certain agent, right? So we are just moving around. So it has a probable randomness of moving from these three states, right? So here it has four Q learning institutions. Whether it can just go here, here, or else it can hit back and come here, or here. So what will be by action here? The action A1 is moving up. For that, it will reach the state 0. If it moves left, sorry, it moves right, it will get A2 state, S0 state with A2 action. If it goes here, it will hit and get back to the same thing. So if it does the A3 action, it will just come back again to the same state. So it will go to this, it will move to the next thing. So for certain action, it has four actions now. Moving forwards, right side, left side, down. So for that, correspondingly, we have some state also, change in state, right? So this is what we just, instead of considering not only the value, we just calculate the state and the corresponding action to attain the state. Okay, suppose see, you can just see the value. Now I'll come to the derivation of Q. We know that, right? We are using Bellman equation. We know that this value of state is the maximum. Okay, so maximum action in which it occurs, right? So maximum action of the reward points of the state and the corresponding action plus discount factor of these, right? So what is this Q? Means quality of learning with respect to the state and the corresponding action does. Okay, so the same thing, it will be same enough. So whenever I just move from this to this, I'll get a reward, right? So if I move here, I will get a reward for certain certain state and for the certain action, right? So I'll be getting a reward, right? Plus I'll be getting the probability of what things I can go. So I can go right, I can go left, I can go top, I can go bottom. I'll get. Wait, what is this? What is this? This equation is something similar, right? So if we just think, if we just look into somewhat deeper, it is nothing but this. So the value of the state is nothing but the maximum action of the quality learning. Okay, so we can rewrite this as the value of state is equal to maximum action of the quality of its learning. So every time the learning increases, the maximum quality is the value of the state. So first time my robot dogs go there and fall. Next time it won't do that. So this is a maximum action. Next time it just changes the direction. Right? So now I want to reduce still more further here, since we are just calculating only quality. So to find the value of next state, right, S prime. So what I'm going to do is I'm going to equate again the same thing here. So what it will be mine. So my quality of a certain state with certain action is equal to reward points times of the probabilityness of the probabilityness of the corresponding values, right? The probabilityness of corresponding values, and the maximum action of the corresponding quality learning of the next step. Okay, so I'm coming again, so you can just see how this explained. So by Bellman's equation, we do have maximum, right? We do have the maximum actions reward points corresponding to the state and its action, right? Plus discount factor times of the probability or the randomness of certain state corresponding actions and its next upcoming state, right? So into its value of the next state, right? The same things, whenever I just go to the quality learning, I'll get reward whenever I just move to the next cell, next sorry state, and then plus the value of this, which if you keenly observe, it is something like the value of the state is something equivalent to the maximum actions quality learning. Okay, when I just try to bring everything in terms of quality learning, I just substitute here, obviously I'll get that. Okay, so what I'm going to do now is I'll just recollect everything as of now. What do we have this today? Okay, so we've just saw about plants, policies, right? Plants, this is a plant, this is our plant, so it will be going around and around, right? We have certain steps here, 1, 0.9, we have things like this, but plan is not only enough, so we move on to the policy, right? So we move on to the policies. For policies means it will just avoid the, totally avoid the uh, getting what to say, getting something like penalties or getting out of the game. It will totally avoid, right? So next what we are seeing is we are assuming some penalties, right? So we are assuming some penalties. Why penalties means we want to avoid the agent to do the maximum steps, not only in game. If we to consider something like we just saw in the before module, um, if you are investing in a share market, it does not want to go to the maximum things, right? So it will just get the smarter way out of it. Okay, it will just try to, based on the conditions, it will try to get a smarter way considering those conditions we keep, right? So what we does is we have a reward points plus and minus one, right? So instead of giving everything, like instead of giving at the end, we just try to give for every state we are giving to give a living penalty. Living penalty means something like it's a reward. Since it is some negative value, we just say penalty. That's the, okay. You don't want to say, so here it was like a R, something like reward. Here you even you are saying R, which is a penalty. That's not a big deal. Since it is a negative value, it's like a reducing value. So we are saying like it is a penalty. Okay. So we have used penalty so that it actually obviously changes its thing, right? So based on the penalty values, if it no penalty, it will just hit here until it here gets the probability of doing that. It will keep on hit. So no penalty, so obviously it will get one. So if we keep some penalty, it will try to move. Don't want to waste things here. So if you increase this, it just moves the things even more stricter. When you keep something like penalty more than this, just try to get into this, because this is even more much better like that is thinking, right? So next we'll move on to the Q learning. Q learning is something but something our agent will be learning at the end of the things, right? So this is what instead of considering only not only the value of the state, we just also consider the corresponding action to achieve the state, right? So that the action will be not only the state, the action will be noted, so that it, if it is not suiting, it will just try to determine something. Okay, so same things we just saw how to derive Q learning part, right? Q learning institution, we just saw how to derive that. Okay, so I got an additional learning for you people. Okay, So I got some additional learning. So you can just look into this. This is something a mark decision processes concept algorithm, so that you can just have this QLearning intuitions. So it will be something related to how come the intuition from the agent and the intuitional values will get correlated upon. Okay, so to know that further, and you to know how the intuition were being fed by the agent when it was given a condition to it, a set of condition to it, how was the intuitions were made, or how are the intuitions were analyzed, and how are the intuitions were being implemented. That's what the basic things around here. Okay, I have attached a link also here, so that if you want you can just use this, right? So I guess this is all fine about this session, and the rest part of this will be continued in the next video. So thank you everyone.